Alrighty. So sorry I missed you Tuesday. These meetings are obnoxious, but hopefully that'll be the only one. So we're going to talk about stacks, queues, and decks, some specialty data structures. Now, I'm not going to do it the way the book does in chapter 6. Uh, he does it great, and it's fantastic and very performant. I find it a little hard to follow. Right, so great, you take a look at it, go through it here, but I'm going to show you the easier way that we're going to build these ones out here. And really, the only reason we're going to talk about these is to look at the performance of them and then to see, hey, is this something that might be a good fit for solving a problem? So we're going to use stacks and queues in one of our projects just to have a good exercise having done it here. But in general, they're specialty data structures here. This is week 5, stacks and queues. Week 5? Yeah, stacks and queues. So the idea with these is we're actually restricting the way in which a user can interact with our data. So right now when we have our Python list, right, our array-based sequence, you can get at something by any index. Right? It's very flexible, very open. Um, some things are slow, right? Like we saw with our lab, inserting at the beginning is going to be slow because a bunch of things have to shift. Removing from the beginning is going to be slow because a bunch of things have to shift. Adding to the end, super fast. Grabbing something off of any location, super fast. So when we look at performance-wise for these things, we talk about their average speed. Now, worst case is important, but again, average is probably more important here. So we're going to look at a class for stack. And what we're going to do with this is we're going to have our own data storage here, and it's just a list. So lists already work. We don't need to use our own version here. We wrote our own version, but again, the list already does everything we need it to do. So when you interact with a stack, you can do 3 things with it, and only 3 things. So imagine you got like a stack of books. You can put something on top, you can take the thing off on the top, or you can look at what's on top without removing it. That's the only things we're allowed to do. So with stacks, we call it push, given an item. So you push an item onto the stack here, and then you can pop an item off the stack. Now this one might sound familiar. We've got pop with lists here, and then you can peek. So peeking just looks at the top item here. And performance-wise for these, peeking, just seeing what's on top is super fast, right? No matter how many items I have, here's the thing that's on top. Give it to you here. For popping an item off, right? To remove the thing at the top here, also going to be constant time on average. Right? Eventually, some things might need to resize here and there, but on average, it's going to be constant time. And then to add something to the stack, because we're using a list behind the scenes, again, adding something to a list here, still constant time on average. So all we need to do then is take our data and we're going to append that item. So you give me an item, I add it to the end of my list. You want to remove an item? Well, that's data.pop, right? That's built right in here. I just give you that item back, right? And we're actually going to, I think we return that item, right? So we're going to return the data pop, right? So take the last thing off the list here. And to peek, we're just going to return self.data at the index of, well, what's the last item here? Well, that's -1, right? That's the last item, should be. So here's the thing here. We'll just give it to you, right? So using the Python list means we don't have to do any extra work for this. And we get really good performance for all of these operations here. Now, this isn't going to solve every problem, though. It only makes sense for things that are put into a stack here. And then we get really good performance. So we're limiting what people can do with all this data that they put into the stack. I don't know if you noticed, when we run our programs, we run in the debug mode, we get this little thing called the call stack on the side that says, hey, here's where we were in the code, and it called this function, and it called this function, and it called this function. That's a stack, right? Because you're only ever working off the top thing. Once you're done with it, take it off, go back to where you were. The next thing on the top, the next thing on the top, the next thing on the top. So internally, computers use stacks all the time. Works out really nice here. And using a stack is one of the ways we can imitate recursion. Right? I think when we looked at that Towers of Hanoi solution without recursion, it uses a stack. And it says, okay, here's the thing I have to do, but I can't do it yet, so do this one here. When I'm done, come back to this one. Right? It put on, hey, I need to move 3 things onto the stack, but you can't move 3, so okay, now it's a call. We have to move 2. We come back to the move 3 thing. So you can imitate that with the stack because that's what the call stack does with recursion. I called my function and it added a call to the stack. It added a call to the stack. It added a call to the stack. So we can do that with these stacks. Now, other things you might want here, you might want to have this length operation and tell you how many items are in your stack. Right? So that's easy. We just return the length of self.data. Yeah. Because I would just want the last thing in the list. So that should be the last item in the list, just because we can do the negative index. I could take the length minus one. Uh, so, and then other things you might want to have here, this is empty here. This is just a nice little helper function so someone can loop through our stack as long as we're not empty doing something. So they add a bunch of things and then they can loop as long as they're not empty to pull them all off. If we've got length, we can also do that. Some people who are stack purists think you shouldn't have a length. You should just know there is something in the stack to do. I don't particularly care here. So we're just going to return length of self.data equals 0. So if our length is 0, empty is true. If our length is not 0, that's false. Right? Um, the other thing we can do is just say not the length, because if it is 0, that's true. Oh, I'm sorry. If it's no, if it's 0, it's false, and anything other than 0 would be true. I think this is probably a little easier to follow here. And again, this one's super fast. So with our stack performance is just really fast. So 0.1 on everything we do with the stack on average. Because we're using the list, we know worst case, eventually you'll have to resize here. But thanks to the magic of averaging and that amortization here, we'll just say on average it's constant. Okay? So stacks are pretty basic, but you can add things to the stack, you can take things off the stack, and that's what you do with them. So when we do our lab on Tuesday, we're going to work with stacks and queues and do some silly things with stacks and queues just to exercise them here before we do our project. But that's all a stack is. So it's limited what we can do, and it's always fast because it's limited. Okay, and then we're going to add a class for queue here. Now a queue is similar to a stack, but our operation is a little bit different. So a queue, imagine you're British here, is just a line. Right? It's a first in, first out, where the stack was the first in, last out, or last in, first out. Right? You only ever did the thing that was on top. The queue or the line, right? Whoever was there first is going to get through first. When you show up, you get added to the end of the line. So we have an enqueue function here that takes an item, and then we have a dequeue function that returns the item at the front here, and then we have a front call that returns the item in the front here. So using a list here is not going to be very performant. And until we get to next week, we don't know a faster way to go about this here, right? Because if we're taking things and adding them to the end, for end queuing, it's really fast. You can always add to the end really fast. But then when you take something off the front, it's really slow. Right? We're like, oh, well, that's sad. It doesn't work well, right? So we're going to get this poor performance. So end queuing, we can get O of 1 here because we're just going to append that item. So self.data data.append the item. But then to dequeue, we're going to return self.data.pop 0. Right? Give me the front thing here. So this one is going to be O of n. The more n I have, the slower this is because I have to shift everything back down to fill that spot here. Right? And then return the front, we're just going to return self.data at 0. Here's the front thing. This one's always fast. O of 1. So when we look at this just using a base list, it's kind of slow. This isn't great here. There's ways we can make it faster though, doing some sort of magic tricks here. Well, not magic tricks, but doing some tricks. So what if instead of removing the item, we just pretend it doesn't exist, right? So we can track here. Here's our self dot front index. Starts at 0, I guess. Really like -1 kind of because we don't have anything. And then when we add an item, if we were empty, now I have something here, right? So we can check, hey, if the length of self.data does not equal 0, or no, if it does equal 0, then we can take our self.front index, set it to 0 here. I guess that's fine. This is kind of messy here. I don't love it. I think maybe we can just get away with it. So we'll just put it at 0 here. And then instead of popping the item off here, wait, let me actually let me go back and do this. So this is the queue class. Let me make another one here just so you can see the differences here. Make a queue. This is a memory eating queue. Okay. So here then we'll take our self.front index is 0. And every time we want to dequeue something, we're going to take here my item is my self.data at that front index, and then we're going to take my self.front index and add 1 to it here. Before we do that, right, I got the item, and then we're going to go assign none here. So grab the item and put a blank in its space. Then go add 1, then we're going to turn that item. So every time we dequeue something, I'm just taking the thing that was in front, giving it to you, and marking it as empty. But can you see why I call this one the memory eating queue? Right? If I add 10 things and take 10 things off, and I add 10 more things, now I really am sized for 20. And I can take those 10 things off, and I can add 10 more things, and now I'm sized for 30. Right? Because we're just never removing those things, we're never cleaning up after ourselves, my list will get bigger and bigger and bigger and bigger and bigger forever. And it's just going to take up more and more and more and more space. But now dequeue, constant, right? Getting something by an index, no matter how many n I have, I can jump right to that index. So essentially what we're doing here is we're trading that space complexity using how much more memory are we going to use to get better performance, to get better speed. And that's what we look at a lot of times when we come to algorithms. What can make this faster? Well, I'm going to trade here. It's going to use more memory, but I'm going to get better performance, right? So if that's a trade-off we're willing to make, great, we can do that. Now, it turns out there are better ways to do this, and we'll get to those later, but we haven't gotten to the next week yet. Just somehow we still move forwards in time, thanks to physics. I don't understand the whole moving backwards in time thing. So we can trade, right? So trading memory usage or performance. Okay, we can do that. Not too bad, right? But can we do better? Of course we can do better. Thanks for asking. Thanks for asking. So we can make this even better here and not eat as much memory here by calling this a circular queue. Circular queue. So we're going to have a front index and we're going to have a back index. Now this gets messy here. So I think with these we need to be tracking them. I'm trying to, oh, goodness. That's what I get for not looking. The book does it in a terrible way and it's really hard to follow and I don't like it. Um, So essentially what we're going to do is we're going to track where our front and back is, right? Kind of like we did with our own resizing with the array-based queue. We're going to track these sorts of things, and then we can grow our storage as needed here. Excuse me. So eventually, when we're dequeuing things and enqueuing things, right, we don't need to go and resize every time because we're going to just go in a big circle here. So let me draw a picture. This is usually a little easier here. I should have brought my tablet for drawing. All right. So if we know we've got a list here, we've got a couple spaces here, 4, 5, and we just start at 5, okay? So if I have 5 things here, and I want to go add something, right? So I've got a front index, I got a back index. When I'm empty, there's nothing here, I go add, a 3. Sorry, that's not a good 3 there. 3, okay? And then I want to add another thing. We'll add, I don't know, a 10. And then EQ the first thing. Okay, now we're going to grab the first thing in line here. So we're going to grab that 3 here. And now my front index moves here. My back index is still here. So this is the front. This is the back. If I want to add another thing here, let's go add, I don't know, an 11. We add 11. Now back is here, right? Front still stays where it is. I can go add a 20 here. My back moves, right? My front stays the same. I can go add another item. Let's add, I don't know, 1. Back moves. Front is still the same. If I want to add one more item now, I don't need to resize my list here because I have room, right? I've got this empty space in front of front here. So it's okay, let's wrap around. Let's pretend this thing is a circle here, and I'll go put, I don't know, let's do 21 over here. Now my back is over here now. Now the next time I want to add something, I'm out of space. I'm going to have to go resize. And I can double my space and copy things over, do those sorts of things here. But now we're not just going to infinitely eat memory. As we remove things, we can reuse that space. So we're going to be more efficient with how much memory we're using, and this is still going to be super fast because it's all index based. So the only downside is we have to track it ourselves, which is no fun. So we're going to start our data as a, what is it, none, I don't know, what do we say, like times 10 or something? We'll just do 10, and that should be fine here. So we've got a front, we've got a back. They're going to start off as none, which is a little bit ugly here, but we need some special handling as we go. So when we enqueue something the very first time, we can say, hey, if self.front index is none, then self.front index is 0, right? Now we finally have something. And then the same if self.back index is none, then self.back index is 0, right? If it's not none, then I need to go increase my back index, right? We need to go see, okay, we're going to move on one more here. But before I can do that, right, I don't want to append anymore. I'm going to set it at a given index here. I need to check and see, right, where is that back index? And where is the length of my list here? So when my back index was over here, and it was index 4, right, 0, 1, 2, 3, 4, that was my last item. The next open spot, right, I had to go see, do I have more room here to wrap around? So we're going to take the back index and we're going to add 1 to it and see if it gets to be more than the length here. Because if it equals the length, I've got to wrap back around, right? So we're going to wrap back around. So we're going to take our self.back index, we're going to add 1 to it, and then if it's equal to the length, we want to go back to 0, right? Well, okay, we can do that pretty quickly, right, with self.back index modulus by the length of self.data, right? Because otherwise, if it equals the length, we get 0. Otherwise, the remainder is just whatever it used, whatever it was, right? You could add an if check if you want, right? We could say, hey, if it equals the length, then set it to 0. Or do you just use this modulus every time? I don't know. One way might be faster. Is it cleaner to say, hey, if the self.back index is equal to the length of self data, self.back index equals 0, right? Is that one better? Instead of using the modulus, this would probably a little cleaner looking here, right? If we now have gotten to the end, jump back to 0, right? We're a circle here, jump back. So we're checking, hey, if we were the very first thing, great. If we're not the very first thing, then the back index has to move. Really, we need to do this only if we have space, right? So we can check if self dot has space, right? Or I don't know, we can just do self dot check for space or something. Let's do that, check or ensure capacity. Doesn't that sound funny? That sounds fancy, capacity. We're going to ensure we have capacity. Add something here. Because we should be able to add as many as we want here. We need to make sure we have room. So we got to go add a little helper function here. Define self dot ensure capacity. So see, do we have enough room to add this? Well, pretty easy to tell if we have enough room to add something by looking at the front and back indexes. But that's kind of awkward to have to track that and to compare them and say, is it always one more, right? If back is here and front is here, we don't have any space. If I add 1 to back, does it equal front? Or I take 1 away from front, does it equal back? But then we have to deal with like the zeros and things like that. It's kind of obnoxious. So it might be nice if we had a self.number of items here. And we were tracking this, right? So we start off at 0, and every time we add an item, let's increase that. Right, so this is all the else case here, ensure capacity, self dot number of items plus 1. Right, every time we enqueue, we're going to add an item. Right, so we can check real quick if self dot number of items is equal to the length of self dot data. Now we're out of space. We got to go resize. Right? If I have 5 things and my length is only 5, there's not room to go add another one. So now we can do that copying. Right? We'll make another one. We'll copy all of them over here. And what's nice with this one is we can stop being this weird circle where my front is in the middle place and my back is in another place here, if we want to. It'll make it a little cleaner if we do. So we can loop from the start, my front index, to the end, to the length of data, copying over to the beginning of the new one. And then we can start at the back, right, and keep on going. So we can go, so our new data equals a list of none times the length of self data times 2, right? We'll just double, right? Do that geometric doubling. So on average, this is always going to be fast. So now I've got twice as many indexes as I need. And then for index copy in range, we're going to start at self.front index. And we're going to range up to the length of self.data, right? So starting whatever the front was up to the end, but not including the end here. We'll take our new data. Now I need that index as well. So our new data index starts at 0. So we're going to take the new data at the new data index, assign it the value of self.data at the index to copy. I know it sounds a little weird, but right, where are we starting? Up until the end, copy to this location here. Now this one's going to auto increment for us, so this one then I just need to add 1 to it every time. Right, so as I'm copying in, copy to 0, copy to 1, copy to 2, copy to 3, copy to 4, as many as I have to copy from the beginning to the end here, right? Now, this might copy more than I need to if we had an end, right, in a different spot. So, even if we're at the beginning, it would copy to the end, and that's good. We should be fine. So we're only going to miss something if the back index, right, was not the length of self data, or that -1, right? So if this was the front here, let's remove some arrows here. So if this was the front and this was the back, we've copied everything. Great, no worries here. If it's not though, so if say maybe this was the front here, and then this was the back, now I have more to copy, right? So I'm going to copy from 0 to wherever the back is, including the back index, right? As long as it's less than the front. Seems a little weird, but so we're going to check. So if my self.back index is less than the self.the front index, right? So if I've wrapped around, right, then I'm going to do this other loop here again. And I'm going to copy now from 0 up to the back index plus 1, because I want to include back index, because that is a valid index I'm going to copy here. We're going to copy to the new data index, wherever it happened to leave off here. From that index, we're going to copy 0, 1, 2, wherever it goes, and keep on incrementing this one, right? So if we've wrapped around, go ahead and copy. If we haven't, that's fine. The first one got it for us already here. No worries. Once all that's done, then I need to reset. So self.front index is 0. And my self.back index is my self.number of items -1. Right? If I have 5 things, the last index is 4, right? Then we're going to say self.data is the new data, right? So we've essentially doubled. We doubled, and then we copied, hopefully in order, from wherever the start is to the end. And then if we've wrapped around, from the start to where the wraparound was, the back was. Okay, and then we reset our values here. A whole lot of extra work to make this circular, right? And then we can double our size, copy everything over. Right? So we're going to ensure our capacity, so we can always go and add something here, right? So if then we've checked here, did we wrap around? Great. We're going to take our self.data at the self.back index and assign it the item, right? So wherever the back was, we've added 1 to it, right? So we were pointed at our last thing. Let's move 1 more space, see if we have to wrap around or not, and put that thing in that new space. Right? And now we've added an item. So I don't need to append anything here. So if the back was none, that was 0. Otherwise, we have to do that. Okay, so then these ones happen no matter what, right? So only does this have to happen if we had a back index, right? So if we didn't have a back index, we had no items yet, I'm going to start at 0, because otherwise, if I start at 0, I'm going to go up to 1, and that's going to be really confusing, right? I only want to do that if I already had something there, here. Okay, so we can always NQ, and then on average, this will always be O of 1, because, we only double geometrically, right? So if we amortize and average that out here, we're fine. A lot of hoops we have to jump through for this one here to make a circular cube, right? But we can always make sure we have room in a way that gives us good performance on average, right? And then we're going to track that circle, saying, hey, if we went around the end here, just go back to 0. If you hit the end, go back to 0, no biggie. And then assign your item, we're good to go. So this is going to be constant here on average. Then to DQ now, we're going to take the item at the front index here, set it to none, increase our front index by 1, but then again, check to see, did we get to the end, right? When we go DQ something. So if the front index hits the end, if self dot front index gets to be the length of the data, reset it back to 0, right? As I start removing things, here, let's remove the front, remove the front, remove the front. Well, now the front index is 5. Oh, well, we can't get to 5. Let's start back here. Go back to 0. So we're still going to get constant time performance on this one here, right? Because it's just a lookup, setting to none, adding to your index, checking it here, resetting it, turning that item. And now we also need to make sure we remove, so self dot number of items -1 here. So we can have a defined length here if we wanted. So we'll return self dot number of items, right? And then we can add it is empty if we wanted here as well, is empty. Now this one is return self dot number of items equals 0, right? If I have 0 items, I'm empty is true. Life is good. Right, so length is still O of 1. Here it is empty is still O of 1. So now we get better performance, and we're not eating extra memory because we're doing some extra work here tracking these front indexes and back indexes as we go, right? Now, when we DQ something, it's possible we take the last item out, which puts us in a weird state here. Right? If we have nothing left, we can't DQ anything. So we might want to check here, like make sure they don't do a bad thing here. So if self dot is empty here, we're going to raise a index error. I don't know, something. We'll just say value error here. Empty. Q is empty. I don't know why I capitalized that. That's weird. Right? If you try and remove something from an empty queue, we shouldn't let you, just to make sure bad stuff doesn't happen. If you want to remove the very last item, fantastic. That's fine. My front will move to wherever the next location was going to be. No worries here. Let me go add items. Right? That should be perfectly fine as we go, because then the back will be the front eventually. Right? If we remove them all. So this one we should test out and make sure it works, right? Because any code we write is worth testing. So should we try it? Oh, so let's make it a circular queue. So I'll have a circular queue equals a circular queue. And then for, I don't know, number in range, let's go 10, let's go 20, right? Because we want to be able to resize and double. And then let's go 21, right? Because it should resize twice at that point, right? We'll take our circular queue and we will NQ the number. And then, how about while circular queue is empty, while not is empty, right? We're going to go print the circular queue dot DQ. Go grab the items, see what happens. Right? And we never removed anything, so maybe we can remove a couple in the middle at some point here, but let's give it a try. It didn't crash. I really thought it was going to crash. Wow. Really expected that not to work. What we got from 0 to 20. Looks pretty good so far. So let's remove a couple items in here, right? So then we'll go, I don't know, circular queue dot DQ. Let's just remove a couple here, and then we'll add a couple more items, right? NQ. Wow, sorry, I should roll the back down here, like 21, 22, 23. So we'll remove a couple things, add a couple things here. That's only going to add to the end. I want to make sure it stays a circle, right? So if we're at 20 here, then we should be able to go add 20, 21, and 22. That should be circular because we made room for them here, right? And then the next one that we add should make it double again in size again. Um, so then we'll add 23, and we'll print them all out. We should get them back in order. Didn't crash, right? 1, 2, 3. So we lost the first three, right? We just threw out 0, 1, and 2. I never printed them here. So it seems like it's working okay for us so far. But let's check. Let's put it in debug mode, right? And watch it work. So in debug mode, we're going to step into our code here. And now we're checking. Okay, so we're going to dequeue. So self here, right, has my data, right? Normal list, right? It hasn't had to resize yet. We're not oversized or anything. Great. We're going to grab all those things, move the front index, return the item. We're going to step over, so I can look at my items here. Right? I've added the nuns. That's what I expect. Added the nuns. So I've got 3 nuns. Now when we enqueue, it should go to this open spot, right? So let's step into this one here, making sure we have room. Front is not none. Back is not none. Back goes up by 1. We are the length of data, so we reset back to 0. And then we go and set. Right? So now the 20 goes here. Life is good so far. Oh, I did the wrong step and now it finished. But it seems like it added it to where it was supposed to go. So we can see we're getting that trade-off. Right? Now, every so often we're using more memory, but Python lists do that automatically, right? Which is sort of a little bit silly because now like it's going to add some padding and we're going to add some padding and whatever. Not the end of the world here. So that's why using your own array-based list is slightly better because the Python list itself is oversized. Remember, we looked at how much memory that thing uses. It's already doing that for us. But again, this works out here, and we're doing this. That's why I think the book is a little more confusing. It does it at that lower level. That it's okay. Um, so that's our queue, or circular queue, right? Pretty good performance on this one, right? We did much better than our regular queue, which was going to be slow on average for dequeuing. We improved that with the memory eating queue. We just said, we'll just use memory forever. And they said, oh, well, we don't need to use it forever. We can reuse that space by being smart here with a circular queue. It's some arithmetic magic, but the arithmetic's not that hard, right? Just when you go back around, just restart. Okay, start using that empty space. Now, the next one we're going to look at, and we're going to base this off the circular queue, is the deck. So the deck is special. I don't know why they pronounce it. It looks like DQ, but it's deck here. It's class DQ. DQ? Oh, now I want Dairy Queen ice cream. Man. So it's essentially a circular queue, or it's essentially a queue, but you can add and remove from the front or the back. So you can add it to the front or you can add it to the back. You can take from the front or you can take from the back. I don't like these things and they confuse me, but sure, you can do those sorts of things. So if we're a circular queue, we're doing the exact same thing here, but now we can end queue on the back or we can add to front. Yeah.
So the is I mean it does the same things certainly with you, but several type of
So our circular queue is still just a queue where the only thing you can do is take from the front and add to the back. So that's the rule with the queue. You take from the front, you add to the back. The deck says, oh, you can take or add from the front, and you can take or add from the back. That's all. So it's just exposing a little bit more here. Maybe in a drive-through, the person who gets in the end of the line, they're waiting and waiting and waiting, decides, you know what, I'm just going to drive off. It's not worth waiting 10 more minutes to get my French fries from McDonald's because they're nasty anyway, right? Whatever it happens to be. So you get a little bit more access to the data. We're still not giving you everything internal. We are a list. So if you wanted the third item, we could give you the third item really quickly. But we don't let you do that. We say, okay, here's the rule. It's first in, first out. But now the deck says, okay, also, if you want to go into the end, go for it here. I don't even know if that one has a term for it here. Um, but same idea here. So it'll work the same way. We just need to manage now that front can move if we're adding to the front by if it front was 2 and we added something to the front, right? Now I need to take it back by 1 to 1, see if there's room here, right? Added in that index, and now I change front to 1. So very similar here. I don't even know if it's worth the exercise of coding all that in here because it's kind of tedious. We could. Right? Why not? Why not? We'll do it. Okay. So now we have this is I don't know, how about NQ front? No, this is NQ back, right? So that adds to the back like we were doing before. DQ from the front, right, is the front one. So we need to be able to add to the front and remove from the back at this point here. So DQing the front. Oh my goodness, my notation got all off here. That's weird. I copy pasted that. How did that happen? Come on, PyCharm. Get good. So I just want all that to line up a little bit nicer. So ensure capacity is still the same. Still copying it's all the same way. So NQing to the back is still the same. So let's go NQ to the front. So that'll be NQ front. Why is it all tabbed in so funny though? What just happened here? There we go. All right, so if we NQ to the front now instead of the back, still need to make sure we're room. We have room. Still make sure all these things are the same here. But now we're not moving the back index. We're going to take the front index -1 here. And then if we got to 0, or if we got to -1, right? Because 0 is okay. If we got to -1, now we need to go and reset the front index to the last index here. So it'll be the length of self.data -1, right? And then we'll set it to that front index, still adding number of items +1. Right? So we should be able to add to the front. Same idea here, right? Make sure we have room. Back up the front index to the next open spot here. And I know I have an open spot because I've ensured capacity. Right? I don't need to check to make sure I'm not going to override or clobber anything here. I know it's going to be open. Maybe I just have to go around the circle, right, to add to the front. And then DQing from the back then is the next one we have to do here. So DQ, why is the tabbing all wrong here? So this is DQ from the back. So make sure we're not empty. Now we've got the back index here. So grab the thing that's in the back and then make it empty, right? And then take our back index -1, right? Because if we were at 5, now it needs to be at 4, right? If we were at 3, it needs to be to 2. So we're shifting it back. We took that back item here now, and then we can check, hey, if we equal -1, equal to -1, then we'll set our back index to the length of self.data -1. Take away the number of items, right? So if it was 5, we go grab the thing at 5, mark it as empty, move back to 4. If it was 0, grab the thing at 0, move back 1. Oh, -1's too far. Loop back around to the end. Right? You should be able to add to either direction here and have it work. We can try it and see. So that was our circular queue. That was all fine. Let's make a deck here. Equals a deck. And then what do we want to do here? Let's just add a couple things. So we can NQ to the front. How about a 1? And we NQ to the back, a 2. We can NQ to the front, a 0, right? And then we can NQ to the back, a 3. So we should get 0, 1, 2, and 3, right? When we get these items back out here. So, right, while it's not empty, we'll print that item while our deck is not empty. We'll take our deck and let's DQ from the front here. And we already did front. Let's DQ from the back. See if we can get it in 3, 2, 1, 0 order, right? 3, 2, 0, 1. I'm kind of amazed that seemed to work. So we were able to remove from the back. So we removed a couple things. Maybe let's just remove one thing. And let's go add some more. So we remove something from the back. Let's add another thing to the front here. How about like -1 should be the front. And then let's add another to the back for fun here. So we removed a 3. Let's jump over to 4. So we should have -1, 0, 1, 2, 4. Right? Uh-oh. Oh, we were going in reverse order. So 4 was the back, and then 2, then 1, 0, -1. I think it's working, friends. I'm kind of amazed it worked. Really thought we'd have to do more debugging because the debugger is your best friend, right? You got to run things step by step by step by step by step and see what they do. It's your best friend. Like, went a little fast here. I apologize, but they're relatively basic ideas. We either have a stack that you work off the top of, or you have a queue that you work off the front of and you add to the back, or you have this deck that can do both sides. So we can use them if they make sense to solve our problem. If it doesn't make sense to solve our problem, we don't use it. We can just use a regular list. But if restricting access works and that's good, great. So if we want to make a class and expose it to someone else, say, hey, my class does this thing, it has a queue of something that it's storing. The only way you can get it is by taking the front item. Sure, right? I usually would do a lab, but it got to be a little bit complex. We pretend we're a uh, four guys, burgers and potatoes or something, right? Obviously not related to any other restaurant chain out there. But you can essentially make a burger and you add it to a queue. Right? They have a bunch of pre-made burgers. You're taking the one that's in front that's been there the longest, right? Because that's hot and delicious. Hopefully not longer than health code says it should be, and I'm sure they check that sort of thing. Ugh. I like that Little Caesars now has to scan their pizzas, and they know if the hot and ready is too old to serve because they tag it in their system. That makes me happy. I don't think burger.
We'll just make them tags, scan everything.
Yeah, I mean, it's so much easier and then foolproof because they don't pay the cashier enough to care. Honestly, the cashier making minimum wage or whatever doesn't care if the pizza's been in the oven an extra 10 minutes or an extra hour. They're going to give you that nasty pizza anyway, and it's okay, right? But if we tag it all, then the system prevents some of those human errors. Be like, oh, I'm sorry, I can't sell this one to you. All right, well, I want a fresh one anyway. I want it hot and ready, not old and lukewarm, right? That sort of thing. So if a queue makes sense, great, we can implement a queue in our system. Hey, you're only ever taking the thing in front. That makes sense. But it's not going to solve all of our problems. It only solves problems that make sense for a queue, those sorts of things. Hey, we want to do a drive through and simulate our drive through and see how long it takes for someone to get served. Right? Okay, well, we're going to add them to the queue of cars. And I can say, okay, when you entered the queue of cars, it was 2:30 p.m. When you were served your food and we dequeued you off the front here, now it was 2:50. You've been waiting 20 minutes. You're going to be pissed at us. Right? It took so long to make your food. I don't know why people go to Culver's. They always have such a long line, and it takes them forever to make food there. I don't know. They always have a line, and then they've got like four parking spaces because it's not actually fast food. But sure. So if it makes sense for these problems, we can use them. We'll be doing a project with these just because we need to exercise them. It's one of the ideas that we can use these stacks and queues here. I think it's in one of the learning outcomes, right? Um, sorting. Oh, it's not specifically in here. Okay, that's all right. But we're going to practice them anyway because they're fun to play with. Uh, that's all. And again, building them from scratch gives us a better appreciation for why they're fast and slow. Um, there's a queue class in Python. Um, it is the collections queue or deck. It's already built in. The fine folks at Python have done this for us. We didn't need to build it ourselves. But again, going through that exercise hopefully helps you understand why it's fast and what it's fast at and what it's slow at here. So this is, we don't want the queue as a list. You can import deck from collections, implementing QQ, a QQ of max size. Get now, put an item. Okay, sure. So we can use a queue. You can even set a max size for that. That's fun here. All right. So we've got them out here. You can play with them. We'll work on those. So we'll do a lab with stacks and queues come Tuesday. And then next week, we'll look at linked lists, which is another way of storing data, which has its own trade-offs of what it's fast at and what it's slow at here. And then we'll actually look at doing stacks and queues with linked lists here, which is kind of fun. And we'll look at what speeds up and what slows down for those sorts of things. And then we'll get into trees. And this is like the generic tree. And then we use trees for priority queues. We use trees for search trees. So like, we'll come back to it again here. We don't go crazy deep into some of these later topics because again, we're going to kind of intro them. You'll pick it up, go further in 350 or data structures, algorithms, analysis class here and have some more fun with these. But we are looking at 2 more weeks after this, spring break, and then midterm review Tuesday. So the tree lab will probably be on 3-3, right? Because we'll finish up trees on the 20th, and then 2 weeks later, after you've forgotten everything and at spring break, then we'll try it in lab. The timing's just a little bit funny, but that's okay. And then we'll do midterm review for lecture time. Thursday, the 5th, will be the midterm day. Like last time, I'll open it up. Really, as long as you get submitted by the 10th, I'm fine. Like, it's not timed, it's open book, open notes, not open neighbor. It's your individual effort. It's not hard. It's a quick little check. Hey, did you get enough stuff out here? It's only worth 10%, which is sort of a lot for one thing, but not a huge amount here. Go know where to go look stuff up. I need to post quizzes for you guys. I'm so sorry. I keep forgetting. I will go grab all the quizzes, put them in. The due dates are pretty flexible. I'll extend the due dates out pretty far because ideally we'll do the quizzes before the midterm because I'll use quiz style questions on the midterm. Okay, so I'll get that in. So we'll have a couple weeks to work on the quizzes here. Um, they're pretty short and quick. That sound good? All right. Anything else? And then don't forget the project we're working on. Right. So we've got checkers as well. Due the 13th, so a week from today. Right. We're gonna go over checkers next week. So good. All right. Thanks, folks. I will see you Tuesday then.